Hi, it's Mr. Roix. I'm going to apologize in advance for the quality of this video. I'm trying to make it while sitting in my car outside of gymnastics. And you might hear cars going by in the background. But I promised you I'd get this out, so here we go. First question is calculate out the initial pH for this particular reaction. All right, and they tell us that the Kb value is 1.8 times 10 to the negative fifth. So, again, since this is a weak base, we are going to treat it just like we would treat a weak acid. So what we'd want to do is we want to do an ice chart, and we'd have our POH going to B and OH. It's an H there. And so initially our concentration is going to be 0.1 molar for that, the base, 0 for the anion, and 0 for the hydroxide. And the change is going to be minus X for the base, plus X for the anion, plus X for the hydroxide. And then our change line is 0.1 minus X plus X, or no, I guess I don't have to show the plus, but it would just be X and then X. So then what we're going to do is put it into the equilibrium expression. We're going to have the concentration of X times the concentration of X, and that's going to be over 0.1 minus X, and that's equal to our Kb value, and the Kb happens to be 1.8 e to the negative fifth. So we're going to solve for this. A couple things, just like we would do with an acid, is we're able to negate this X. So really we have X squared over 0.1 is equal to 1.8 e to the negative fifth. If we solve for that, we're going to get X squared is equal to 1.8 e to the negative sixth. And we square root both sides. If we square root both sides, we're going to get X is equal to 1.34 e to the negative third. Now, since this is a Kb expression, X really stands for the concentration of hydroxide ions. So if we want to come up with the initial pH, what we need to do is we can solve for POH. So we do the negative log of this value, and then that is going to come out to be an answer of, what does that come out to be? POH comes out to be 2.87. Now again, we are solving for pH, so we want to look at the difference between this value and 14. And so our pH is going to be 11.13. So that is the pH, the initial pH for this weak base. Question 2 asks, why is the pH greater, or excuse me, why is the pH less than 7 at the equivalence point? The reason why the pH is going to be less than 7 at the equivalence point is because ammonia is a weak base. And just like we talked about with weak acids having strong conjugate bases, ammonia being a weak base has a strong conjugate acid. So the ammonium that forms to produce the weak base can go back, and I'll write out this equation here. And so what ends up happening is the NH4 is going to basically give the hydrogen back to HCl, producing those acidic ions, and that's why the pH, the equivalence point, is going to be less than 7. It's going to be in the acidic range. 3, we're not going to worry about calculating out the pH at the equivalence point. Don't worry about that. And then 4, the last thing is, what is the pH halfway to the equivalence point? And if you remember from discussions in class and earlier on the same worksheet, we said that the halfway to the equivalence point is going to be, that pH is going to be equal to the Ka, or in this case the Kb. So what we're going to do is we're going to set up our expression. Again, we're going to take 1.8 times 10 to the negative 5th, and we're going to take the negative log of that. If we take the negative log of 1.8, I apologize for the extra marks on there, I didn't erase very well, e to the negative 5th, right? That's going to give us the pOH, because this was a Kb, and the pOH is going to be 4.74. All right. Now, if we want to know the pH, we're going to do 14 minus the pOH, right? Because pH plus pOH is equal to 14. So we'll do 14 minus 4.74, and that is going to give us a pH of 9.26. So that is the pH of our solution halfway to the equivalence point. All right, I hope this helped. Again, I apologize for the hopefully it was clear enough, and we'll see you in class.